Hello and welcome to my talk today. I am Anusua Trivedi. I am a senior data scientist in the Microsoft's Algorithm and Data Science group. And we are a partner-facing group, and we actually try and develop algorithms to solve problems which are very customer-specific problems using machine learning and other algorithmic approaches. So today I'll be talking about deep learning. That's my area of forte. I'll be showing you how transfer learning and fine-tuning deep convolution neural networks can lead to reusability of the model that you train. So I'll just give out a small talk outline. So I'll touch on traditional machine learning, and I'll discuss how traditional machine learning is different from deep learning. Then we'll discuss why deep learning is at all needed. And then we'll dive deep into deep convolutional networks, transfer learning and fine-tuning of deep convolutional networks. We'll move on to recurrent neural networks, and I'll use two case studies to show you the reusability of a deep learning model. So first to start with, what is machine learning, or we commonly known as ML? So machine learning and predictive analytics are the core capabilities which drive business decisions. So people nowadays, it's not, depending on any domain, people use machine learning to some extent or the other. So let's take the example of any retail customer. They use recommendation engine to some extent, or to a very, very detailed extent, like context-based and stuff like that. So if you're any retail customer, you have to use machine learning recommendation to some extent or the other. We have been hearing about predictive analytics and machine learning for a long time now. But it's very difficult to actually work with unstructured data like images, texts. It requires any of your traditional machine learning algorithms, it requires your data processing in a particular format. So you need to spend a lot of time preparing your data. In today's world, where we are generating data by second and like loads and loads of data, we need much higher computation power. So it should be able to get the raw data inside, somehow apply the machine learning algorithm, and then give out the analysis results to you. So let's take the example of vision analytics, right? People have been using machine learning with vision for a very long time. Learning and fine-tuning at all? No, right? Okay, that's good. Otherwise, I'll be just repeating what you have done. Okay, feel free to interrupt me at any point of time. Need not wait until the end, okay? I was talking about vision analytics, okay? So people actually have been using images for a long time with machine learning algorithms, but it requires a very intensive pre-processing step. So like, take the example of medical images. People have been using the traditional SVM algorithm for a long time to classify actually the diseases from any medical image. But it is a huge process. If you go and search for papers in PubMed, there are lots and lots of papers which tell you how to pre-process the image, apply filter, get rid of the noise, and it's a whole study in itself, the whole image processing thing. So just to actually make it more simple, and with the advent of more computation power, that is with the advent of NVIDIA's GPUs, we can now use a long existing, like it was existing, deep learning algorithms are nothing new. It was existing for a long time now, even before I was born. So people are now being able to use it to the full extent and actually reduce the time required to compute and train this complex data. Okay, let's formalize what I said. Traditional machine learning requires manual feature extraction and engineering. So I think my previous speaker actually spoke about manual feature extraction and engineering. So, and you all are aware of it. So, and feature extraction for unstructured data is very complex. As I just explained, it's very, very complex. It takes a lot of time and a lot of subject matter expertise. Deep learning can automatically learn features in data, well, automatically in quotes, because obviously you need to give some kind of manual intervention in there. That's where your expertise in designing the network comes in. Like how many layers you need, what kind of network you need. That's where it comes in. But definitely, we can absolutely skip the manual feature extraction step. Deep learning is a largely black box technique, so if you do not want to learn about the network at all, you can just use it, just like a black box. I mean, what we are trying to do here in Microsoft is we are trying to give out APIs. Have you guys heard of cognitive APIs? No, right? So yeah, it's a very new thing. The cognitive API and the bot framework are two new things which Microsoft has come up with. And there are all of our deep learning algorithms running at the back end. So you can just call those APIs and just use it, just as any software developer would be able to use it. So I'll talk about it. I'll show you some demos if I have time. So let's stick with it for the theoretical part before we get to the fun part. So it updates the deep learning, the deep neural network updates learned weights at each layer. So it learns in layers. That's why it's more efficient, more accurate. So why do we need deep learning for image analysis? The things which I said, image data requires subject matter expertise to extract key features. Deep learning, whereas extracts it automatically from any domain-specific languages without any feature engineering technique. So this makes the image analysis process much easier. So imagine you are not a person who has any kind of biology background. So you do not know anything about medicine, you do not know anything about angiography, MRI, anything. Okay? So now you are given some MRIs or some angiographic images. So, and you said, hey, can you draw some analysis out of it? Can you tell me if this person has diabetic retinopathy or not, or whether if this person is more prone to having stroke or not? So as an engineer, we all need to be ready for anything like that. Deep learning has made this thing much, much easier. All these people, let me go to the early work stuff. So first, something like neural network came in the paper Neocognitron. And you can go back and refer to the papers. It's very interesting read. And then Jan LeCun actually in 1889 first came up with the concept of convolutional neural networks. With the advent of GPUs, so these were there for a very long time. It's just that our computation power was not that efficient to actually implement in a large-scale basis. With the advent of the GPUs and actually Fei-Fei Li and Brian Catanzaro of NVIDIA, they actually jointly developed CUDA and cuDNN packages specifically for deep learning, and that is actually the reason behind the popularity of today's deep learning algorithms. So the most popular, obviously, is the AlexNet, which was trained on ImageNet images. Actually, the best part about it was trained on Caffe, and Caffe Model Zoo made the trained weights publicly available. So you can actually go to Caffe Model Zoo and download the ImageNet train. So ImageNet is a data set of 1,000 images, natural images, like any scene, scenery, and then there is animals, there is cars, there is clothes, any natural image that you can think of. Not any special image, remember, there is nothing like angiographic image, no MRI, no CT scan, nothing like that, no special domain-specific image. Any natural image, like 1,000 of them level-trained images were actually trained for many days, and the network Alex Rogowski created was AlexNet. So that became very popular, and the trained weights were actually made public. That actually brings me to my topic of transfer learning and fine tuning. How we can utilize. So it's really very difficult to train the initial layers of a deep convolution network layer, because you need to. It can scale up and there's overflow. It can just scale down and never converge. So the initial weights depends a lot on your data. If you have some trained weights to be used as your initial weights, it actually helps the model to converge much earlier. So that's where the transfer learning comes, right? So we transfer some previous learnings into the domain-specific model, which we are going to create, and we fine-tune. Fine-tune is changing the network. So for ImageNet, there were 1,000 labels, 1,000 output labels. Now what we say, okay, we do not want 1,000. We just want to predict if it's a cat or a dog, just 2 of them. Just add a binary classifier at the end of the network. And then, bam, you have cats and dogs. And you need to modify your network accordingly. But you keep all the weights exactly the same, just your input source changes, and you change the classifier. So instead of 1,000, now you're doing a binary classification at the end of your network. Okay, so let's do some formal definitions. So what is deep neural network? It trains networks in many layers. So multiple layers work to build an improved feature space. So obviously we learn in layers, so we learn lots and lots of feature over time. The first layer learns the first order of features. So this is very important in our fine-tuning task. So what I say is there are different layers. So for the first is you're getting some input inside, and the first layer actually learns only about colors, very basic about the image, the colors, the edges, the keystrokes, the hue, those kind of stuff. And to me, there is no such color difference between a domain-specific image and a natural image. Orange is an orange everywhere. Okay, it's just that if I have an angiographic image, I'll have almost the whole image as orange, whereas I have a natural image of a person wearing an orange t-shirt, that will be just the person's body, upper part of the body saying it's orange. So it's very easy to actually get the color perceptions out. So now I ask you, if I've trained my model on a natural language, on natural images, now if I keep the first layers fixed and fine-tune the lower layers, which becomes more domain-specific, that suffices, right? I mean, it has already learned about the color, the stroke, and everything. So I need not train the whole 8 layers. I'll just train the last 4 or 5 layers maybe. So let's see how I do it. So the second layer onwards, it learns the higher order features, okay? And lastly, the final layer features are fed into supervised layers. As I said, it is already being fed into a ReLU or a softmax classifier. You can add another binary classifier on top of it, whatever suits your need. Okay, so deep convolution neural network. This is how traditionally the model looks like. So that's the input. Okay, I was told to move the mouse pointer. So this is the input image, and these are the convolution layers. From the convolution layer, you actually downsample to the pooling layer, and then you again move out to the second layer of. So what happens at deep convolution layer is it learns in 2 stages. First, it tries to apply a filter or weight to every convolution layer, and then it goes to the end of the network, okay? And then it does a back propagation. It actually learns when it does a back propagation, where it has made some changes based on the features that was available at the end. And it tries to modify the filter accordingly. Then it takes the next segment input data and tries to apply it to the modified back propagation filter weight. And then again, it comes back and sees how it needs to modify the weight or the filter. So the backward and the forward propagation is something. Initially, I was talking about deep neural network. This is deep convolution neural network. So we learn forward propagation and backward propagation, 2 stages. Okay, so yes.
Filters for the first convolution layer, even with the new images, will they stay?
So that's what the initial weights are. I said, right? It is very much image dependent. So that's where the expertise of a model maker or a data scientist comes in, where you actually have to initialize the weight correctly. If you do not use it correctly, there's a chance that after 15 iterations, it will just overflow. It overflows a memory. Or after even 15,000 iterations, it never converges. So it's very essential to actually do the correct. That's the step we're actually trying to skip by using the transfer learning, so that anybody, I mean, not a data scientist who do not have any algorithmic experience, can actually use deep learning to make a software development application. Okay? Yes.
So backprop seems computationally more expensive. So, I mean, is there a way to control how much forward propagation versus backprop?
No, what I do not understand what you mean by computationally intensive, but there is a new thing which came up in NVIDIA. They introduced something called the VDNN. It's a very new paper, and they actually have reduced the computation by almost 7 to 8 times by introducing VDNN. So just go and read about it. It is actually, so I'll just touch it. So what you do is, when you learn, you produce lots and lots of image features, right? Every convolution layer, it actually increases multiple times the features that you're producing out. What VDNN does is actually copies it through the PCI to the main memory and keeps it there. And it frees up a lot of memory space so that it performs much better. It's way more faster. When it's coming back, it brings back the weights on demand. So it's a completely architectural thing. And it's really interesting how I knew it. But yeah, let's talk about that later. So that's, yes. Oh, the deep stands for, so the question was, what is the deep stands for in deep convolution network? So if it's more than 2 layers of convolution, it's called deep. That's what I'm saying. If there are 2 convolution neural nets, then it's called convolution neural nets. If there are more than 2 convolutional layers, it's called deep convolutional layer. Okay, so there are 2 main features in a convolution layer. It's called convolution and it's pooling. Okay, let's look at them. So this is how a convolution is working in the left image. So this is an input image, and this is a filter, that is the weight, as I said, you apply. And you try to multiply it, right? So because this place is just the 1, so only 42 is a valid number which comes out of it, right? Everything becomes sparse because I multiply all the numbers with 0, right? And that's how we create a huge sparse matrix, right? That is and we take each and every segment. So like we take the first 4 and then the next 4, and we then take the next 4, and we take it in segments. And that's why when we do a convolution, if the input image is like this, we get like 8 or 16, depending on the squares that we are selecting. And convolution layers consist of rectangular grid of neurons, so we call these neurons. The weights for this are the same for each neuron in the convolution layer. The convolution layer weights specify the convolution filter, as I just said. These are called the weights or the filter. They are interchangeably used. Okay, let's go to pooling. The pooling layer takes small rectangular blocks from the convolution layer and subsamples it to produce a single output from that block. So here we are doing max pooling. So what I'm doing is, there's the first rectangle, so I'm pulling the first one out, so it's 6. And on the second rectangle, the max one out, 8. From the third one, the yellow, it's a 3, and from the blue one, it's 4, okay? So that way, we're just downsampling. So we have actually blown up our feature space by magnitudes because we multiplied it by feature vectors, right? By weights. So now we need to downsample it. That's what the pooling layer is, a downsampling.
Are we like using information in this step?
No, that's why we learn in cycles, right? That's why it's not just one thing. So when it learns, if it's your face it's learning about, you just take this part of the pixel first, then learn about it. Then it take the next pixel and it does, like, it takes like small rectangular portions where there are a small amount of pixels, and it learns recursively. That's why it takes so long to train a neural network, any deep neural network, because the deeper it is, there are more convolution and pooling, and you are going precise. That's why it increases. Deep ones are more precise than the natural ones, as she was asking. So why we use deep? Because it's more accurate, it's more precise. But the drawback, it takes a long time to actually train it. How do we improve it? By transfer learning and fine tuning, because we are keeping the initial layers fixed, so we need less layers to modify, okay? It's a VGGNet, it's a 16 layers or 19 layers, it takes forever. I mean, I tried it using a 4 GB, in Theano I tried with a 4 GB GPU. I couldn't train it. It minimum requires 24 GB memory capacity for a GPU. So you can only train it on a GPU cluster. So that's why if you're using an already trained VGGNet, that is possible using a 4 GB GPU. So that's actually giving you the performance as well as the accuracy. Okay, so this is Jan LeCun's model. This is just a DCNN sample. If you have a handwritten digit out there, the 32 cross 32 input image, you actually blow it up by convolution and then downsample it. And from the S2 layer here, I'm multiplying it with a sparse matrix, and then I'm getting C3. So I'm multiplying S2 with sparse matrix like this, and I'm getting this 16 layers, right? So I have 6 downsampled layer, and then multiplying it again, and getting 16 convolution layer. And again, I do some downsampling, and I continue doing this in different cycles. Okay, transfer learning and fine tuning. Convolution neural network, this is an image taken from, again, Alex Rogolsky's paper. So it has been trained on thousands to millions of labeled images. And as you can see, there are multiple outputs. Essentially, there are 1,000 outputs of ImageNet. So it's car, truck, cat, dog, bicycle, then whatever, like a hat or dress, things like that. There are multiple categories. Suppose you want to learn only about car and truck, or cat and dog, or cat, dog, bird, not only binary, any number of times, any number of output, but just not 1,000, maybe less, maybe more. I mean, you can actually blow it up too. But the thing is, we actually use the pre-trained CNN and use it as an initial weight, and then we fine-tune the network weights, but we are actually training fewer networks because we have fixed some weights, and we are doing the transfer learning here, okay? Let's see what actually I'm using, what framework. So there are many, many deep learning frameworks available nowadays. I'll be talking about the open source ones. So there are non-symbolic frameworks and symbolic frameworks. The main drawback of non-symbolic or imperative frameworks are Torch, which are like Torch Cafe. It actually requires manual optimization. So it's not very helpful if you want to modify it, right? In transfer learning, we want to modify it. So if you are using Cafe or Torch, it's not very easily modifiable. So it's fine if you have a trained model and you're just testing on that trained model. It will work maybe better than Theano, maybe much better than Theano. But the problem with Cafe or Torch is it is very hard to modify. Symbolic frameworks like Theano, TensorFlow, CNTK, Microsoft Deep Learning Framework, ImageNet, which supports R, actually can infer optimization automatically from the dependency graph. And the symbolic framework can exploit much more memory reuse. So it is easily modifiable, the memory is reusable, and there are many more other plus points. I'll be using Theano for my work here. So it's easy to implement to create new networks and also to modify existing networks. It has got high-level language support. It has got Lisnani and Keras. So it is, if you are a Python user, even if you're a Python developer, you can just go and play with it and modify it very easily. You need not understand down to like tensors and the multi-pronged approach. That can actually trigger your brain a little bit, but yeah, you need not touch that. It's very easy to just modify using the Python layer, especially if you're using Keras. It's easy to customize in a very domain-specific data, I'll show you. And transfer learning and fine-tuning is very easy because it's very easily modifiable. So the first case study, which I will talk about, is the diabetic retinopathy prediction. If you're a Kaggle user, you must have seen this data multiple times. If not, welcome. It's a very heavily used sample data set from Kaggle. We use labeled fluorescent angiographic images of eyes to improve diabetic retinopathy prediction. So let me talk a little bit about diabetic retinopathy. So 80% of the vision loss in America is due to diabetic retinopathy. People who get diabetes actually are 90% prone to get diabetic retinopathy prediction and complete vision loss. So it's very essential to actually try and predict diabetic retinopathy at a much earlier stage. There are 4 stages of diabetic retinopathy. So it's mild, medium, high, and prolific. Once it's prolific, you lose your vision. So it's very essential that you start your treatment in mild or medium stage. Past the medium stage, actually the treatment does not work that well. So fluorescent angiography is nothing but they inject a dye called fluorescein in your eyes, and it dilates the blood vessels. So if there is a rupture, so basically what happens in diabetic retinopathy is it actually dilates and ruptures, and your eyes bleed, and there is complete vision loss. So it can look at the diameter of the when you give the dye, you can actually look at the diameter of the blood vessels and how dilated they are. So that's how you actually recognize at which stage of diabetic retinopathy your patient is in. And we'll use a deep convolution neural network to improve this diabetic retinopathy prediction. We'll use GoogleNet, again, a very commonly used network by Google. It was built on top of, inspired by LeNet, and it performs better. I think it performs better. There is, and I use ImageNet pre-trained GoogleNet. So ImageNet are these natural images: flower, animals, ships, pumpkin, Halloween pumpkins, dogs. So these are actually, on the left, it's the prediction accuracy. So if you upload a picture of a leopard, it actually correctly says leopard. And the second highmost prediction is jaguar. So it's not saying just a cat. So it learns pretty accurately because jaguar and leopards are different in their patterns of the black spots, and it can go to that fine grain of the picture and understand how different the black spots are, and actually can say whether if it's a jaguar or a leopard. So we in Microsoft have been using this mechanism to verify which are the male and the female giraffes. So there is pattern, they have different black spot patterns. So it was becoming essential for the national park in Africa to actually track why the female giraffe population is going down. So so there is a blog available and how they have done it. So definitely go and check it out. So transfer learning and fine-tuning our deep learning model. So we use first, an ImageNet pre-trained model. We fine-tune that DCNN to transfer generically learned feature to diabetic retinopathy prediction. The lower layers of the pre-trained DCNN contain generic features that can be used by the DR prediction task. Let's look at it. So just by looking at it, you cannot say, right, which one is diabetic retinopathic and which one is not. I mean, the one on this one looks like it's more dilated, more spotty, so you can say it's diabetic retinopathy, but so is this one, right? So you cannot say that there is this pair is diabetic retinopathic or this pair. So, oh no, I'll show you. Just give me a minute. The upper layer, whole of them are diabetic retinopathic. Even this one is diabetic retinopathic. And the lower layer, everything is non-diabetic retinopathic, even the one which is spotty, right? So it depends, actually, it depends on the fine dilation of the blood vessel, which is not actually very easily perceived by natural human eye. Obviously, doctors are trained for many, many years. That's why we go to doctors and show them our MRIs or angiographic images. But we cannot say which one is what. Even if the machine is predicting wrong, cannot say what it is predicting wrong, whether if it's correct or not. So it's very essential to do it very correctly, almost close to 100%, because it's medical data and the medical analysis will depend on it. So there is no filtering process. There is no noise canceling. There is no application of colored filter. We want to keep the color intact, right? But the problem, one very big problem of deep learning is it requires lots and lots of data to be trained. Okay? It requires a huge, because ImageNet is million images. It's very difficult to get like labeled domain-specific images. So it's not possible. I mean, I can say that this is maybe the only diabetic retinopathic image set which they have created and made open source in Kaggle. Even if it is, it has got PII data, it's held restrictively by hospitals. So we have a heart stroke data which we work with in Texas Hospital, but it's proprietary, they do not release it. So it's very difficult to get very small domain-specific data set. So what we do is we augment the image and increase the corpus size. By augmentation, I mean I just rotate the images. Okay, so there is 0 degree. I make 90 degree, 270 degree, 180 degree, and then 270 degree. So by just rotating the images, and it's very essential if you're learning about humans, right? If I stand like this, my hands are up and my legs are down. If I show a pic, and I train only on me standing upright. And then I show, as a test image, I show my computer of me standing on my hands, which I cannot, but still. Yeah, if I'm standing on my hands, and it will say, oh, hey, I think this is the legs, and this is the hands, and this is the legs, because it knows that direction and orientation only. So it's very essential to make your model very, very accurate to use image augmentation. So it learns in different angles, and the colors also depend in different angles, so it differs. So it learns colors, hues, in different angles. Yes?
For pictures, how big can pictures be such that, like you can't have like a 1 megapixel picture, right?
Yes. So I have used 24 cross 24. But yeah, I think that is the minimum one should go to, so that you retain the original color and the hue, the intensity, and everything. You can obviously train smaller, but obviously if your data in is bad, then your data out will not be that much accurate, right? The smallest one which we do, I mean, which we upload in the cognitive APIs, which we have made public, is 50 cross 50. But I have used 24 cross 24, and it has worked really well still. So it varies. I would suggest not going below 24 cross 24, and also not use 1000 by 1000, because it will take like forever to train your neural network, because it takes your image in segments, right? In pixel segments. So do not use 1000 by 1000. Maybe 50 by 50, or maybe 100 by 100 is the max you can use. Okay.
So all these models that big companies have, they're really squeezing out a picture into like 100 by 100 maximally.
Depends actually. If you have a huge GPU cluster, I'm talking about individual contributors. If you have a huge GPU cluster, so I used to work for a supercomputer center, and we had this big GPU cluster. It was a supercomputer. So if you have something like that available, obviously go ahead and use 1000 by 1000, whatever you want. But just for individual contributors, or to get something done very quickly, definitely a smaller size picture, but retaining the information is very important. And that's where you need to take the call. Yeah.
But in some of these domain-specific images,
Yes.
you can't afford to lose information by downsampling, right? Like if it's a CAT scan, it's got a lot of features inside it.
No, you keep the aspect ratio. You keep the. So the essential thing is to keep the aspect ratio same. Do not change the aspect ratio. If you change the aspect ratio, there is a chance of, losing data in one dimension. So whatever way you shrink your data, you actually, obviously in the case of 98%, you will get 97 or 96% accuracy. But that's the compromise you're making so that you can complete your task in time. Okay, that was image augmentation. How much time I have? Oh, my 5 minutes. Okay, I'll try to go fast. Okay, so this is where I'm doing transfer learning. So here it's 0 degree, the red one. The green one is 90 degree. This one is, purple one is 180 degree and 270 degree. So I input images in multiple dimensions and this is convolution pooling, and then I apply a binary classifier here, and I get diabetic retinopathic or non-diabetic retinopathic, okay? So that is transfer learning because I keep the initial weights same here, and then I apply the final layers I change, okay? Okay, next I come to fine tuning, okay? So I fix the first two convolution layers because I said I'll be using the ImageNet trained initial weights. So I fix the first two convolution layers, then I fine tune all other layers, and then I add new layer for a binary classification. And that's how I'm getting non-diabetic retinopathic and diabetic retinopathic, okay? That's all I'm changing. Yes? Yes, the lower layers. That's what I said. It was in the slide. You need to keep the lower layers because that's the first layers you hit, and those are the layers that takes most of the time to get trained because it's seeing an image for the first time, and it tries to. Those are the layers which actually learns about colors, keystrokes, angles, and things like that. And because it has no prior knowledge about the images, those are the layers actually takes most of the time to learn or to train. So if you fix those layers there and train so it has some prior knowledge about, okay, if I see this pattern, this is blue, this is green, and it knows what the pattern to look for. Yes?
So where do you introduce your retina images?
Oh, that's the input.
The first two layers are based on
That's when I say fixed, I say the weights.
the weights.
The weights are
The
fixed.
images.
Yes. I do not do a forward and backward propagation on the weight images. But obviously, the input is coming and feeding, and the multiplication is being done by already pre-trained filters or weights. Okay. Okay, this is diabetic retinopathic prediction outcome. So I tried all the green ones where it was able to predict diabetic retinopathy correctly. And all the red ones, it did wrong. It said, no, it's not diabetic retinopathy. So as you can see, out of I actually gave 25, but out of 100 images, only 3 were wrong. So that is a good percentage that I was getting. And the more you train, you get more accuracy. So this was the first, I think I trained it for I think 50 iterations, and this was the outcome.
Question.
Yes.
Can the doctors accurately predict if it's a DR case from such a low-res image? You said you're using 240 by 24 pixels.
24 by 24.
24 by 24?
Yes, 24 by 24.
Mist dataset.
Like MNIST, yes, like MNIST dataset, really low. But as I said, if you keep the aspect ratio correct, and it took me about a week to train it, but because I was using just one GPU or 4 GB. If you're using multiple GPUs, you would be able to train it within 3 days, I'm hoping. So, and that's not bad to get 96% accuracy with that.
My question is whether the doctors were able to tell if it's a DR case or not.
Yes, not with the DR, but the one which we worked on with the Texas hospital, the stroke data, which is not public. Yes, obviously you need a ground truth, and in medical image analysis, doctors are the ground truth.
Can
So.
it tell from such a low-res image?
Yes, it can because it learns in iterations and it learns multiple times and it autocorrects itself as it learns. So our DCNN improves DR prediction accuracy compared to the state of the art. Obviously, to come back to your question, if you increase the image resolution, obviously it will get to this accuracy much more faster. But then to train it over a bigger network layer, it will take a lot of time. Okay, so you need more computation power to come to this accuracy in the same amount of time. If you increase the computation power, it will work. Okay. So our DCNN improves DR prediction accuracy compared to the state-of-the-art SVM approaches. So people have been using SVM. You can find papers in PubMed. Yes?
I have a concern in the data balances. So how is the balance of the classes for the...
That's a good question. Yes.
You're using accuracy, right?
Yes. The balance was not a good balanced data. So we had to balance it by taking like almost equal proportions, trying to get like if I take 25% of diabetic retinopathy, I try to take 75% of non-diabetic retinopathy because there were no more cases of non-diabetic retinopathy than diabetic retinopathy. So that's why I was trying to predict and see if it can correctly predict diabetic retinopathy, right? Because it can overfit a non-diabetic retinopathy instead of diabetic retinopathy.
Is it then better to take precision or recall?
Yes, it is. It is precision, and I took that one and plotted it too. But I am here just showing you the mean accuracy. I mean, that's what people mostly generally relate to, right? Even if you're showing it to your doctors, they're like, "Oh, what's the accuracy level of your model?" So that's most people. Yeah. So when you're showing it to your end customer or your end users, that's the best thing which they understand. They're not. Yes, separate.
Test set was
Separate. Yes.
balanced or
Sorry.
was your test set balanced or severely?
Oh, that's what I said. I tried to balance it. I tried to balance it. Yes, manually do it. I mean, select this person, and then try to test it. I mean, there is a validation set, and then when I tried to test it, train it, and then use a balanced validation set, and then change the network accordingly if it did not do well. I mean, it needed to increase the training set once or twice so that it becomes more balanced. And then when I tested it on the test set, the results that I'm showing, that's the result I got you. Okay, other uses of this same DCNN model, obviously we can use it on CT scans. We can use on USGs, ultrasonograms, this one. We can use it on a spine CT scan. We can use this on even a natural image if you take it with a picture. So it's showing whether if its mole is a carcinogenic or not. So once you have trained those weights, of this model, what you can do is you can just change the input set, because we have already trained it on a medical data set, it knows how medical data sets work, how actually the color and the hue of medical images will change. So you can keep, like, instead of 2, you can keep 4 layer weights same, and then train maybe the next 4 layers if it's a 8-layer network. Okay, so that's how it works. We are trying to use progressively. So I use ImageNet on diabetic retinopathic prediction, and then I'm using that initial trained weight and fixing the 4-layer weight and reducing the number of layers I need to train. So the more specific, so if I've been using, these are where it will work, but the best will be if I'm using another fluorescent angiographic image of a heart maybe, because it's the same color and hue, so it will be bam, you just need to train the last layer and it will work very good. Okay? Okay, so reusability of this DCNN model, I do not think I have time, but I'll try. So we can fine-tune ImageNet trained DCNN for medical image analysis, as I showed you. We can fine-tune the same ImageNet trained DCNN model in a completely different domain and for a completely different task. Okay, so let's see how. So fashion image caption generation. Okay, we use the ImageNet trained DCNN to learn apparent classification with style, which is known as ACS. You can go and look up. ACS is a data set which actually has labeled fashion images. So you can train it on ImageNet pre-trained model, like we did for diabetic retinopathic prediction, and get the image features through transfer learning and fine-tuning. Now that we have the transfer learning and fine-tuning features available, we feed it to a recurrent neural network. Okay, so we use a long LSTM RNN on the learned image features for image caption generation. It is a stateful model. It learns in cycles, and it's able to generate captions for you using the features that you retrieved from the images. Yes?
What is the sequence of features that you're training the RNN on?
The RNN model? Yeah, I'll show it in image. Okay. So similarly, I do image augmentation of a cloth, and similarly, I do the rotation and then the transfer learning as we showed. As you can already see in the presentation itself, there is overlap. That means the model is very easy to do. Okay. So the recurrent neural network, I'll just define it 1 second. The recurrent neural networks are networks with loops in them, allowing informations to persist. LSTM networks are a special kind of RNN capable of learning long-term dependencies, so it can save the state. So good for statewise step-by-step caption generation task. This one, what you would do, I'm doing is I'm feeding the image to a GoogleNet and doing the DCNN. GoogleNet is what does the DCNN, Deep Convolution Neural Network, taking it to a LSTM layer and learning in stages. So first level, and I get a prediction task. when I forward it, I forward the information in the LSTM feature layer and the predicted task, okay? In here, when I forward this one and this one, okay? So, and it saves my predicted task in the earlier layer, takes it to the next layer, learn more features, modifies the tag, then takes the predicted tag and some more feature and does it in different sections. Okay, this is the ACS image caption generation thing. So actually, the deep CNN, DCNN, which I showed you, we do it. We then generate labels using RNN, and the generated tag for each stage are velvet, blouse, uniform, red, and checks. Okay. So the caption generation, I trained the model and I tried to generate caption using ImageNet trained RNN, GoogleNet, and then feed it without any transfer learning or fine tuning. This image gave me just Windsor tie. Okay. But when I actually applied fine-tuning and transfer learning on actual ACS image set, trained it on ACS image set using the ImageNet pre-trained model weights, it gave me jersey, t-shirt for upper body, suit of clothes. Okay, so much better type of prediction. So it actually is getting that there are two types of clothes. There is t-shirt for upper body, and there is suit of clothes. So there, it actually recognizes two different things and tries to combine them and give the prediction out. Okay, and there is obviously Microsoft Cognitive Services and APIs. Please go and play with it. I do not have time to do the demo, but it's really very cool. Feel free to drop an email. My deck has my email if you have questions about cognitive APIs and bots. All the model that I showed you is just a one-click thing because we have just released it, and any software developer can actually use it. So play with it, have fun, and thanks, and I'm ready to take any questions. Yes?
So are the pictures you're training, are they usually square? So let's say if they're non-square and you want the aspect ratio, you just cut out a square?
Yes, because it's better too, because I said the aspect ratio should be the same. So if it's same, then it's always square, right? So it's 50 by 50. Never do 50 by 100. Well, you can, but it will actually mess up your color and yeah. So it's better not to do it. Yes?
So for the RNN, you're feeding the output of the last layer into the next layer.
Mm-hmm.
So how is this different from the stacked LSTM layers?
How is it different from?
From just stacked layers of LSTMs?
And what would you feed the LSTM? Yes, that's what I'm doing. GoogleNet is doing the. GoogleNet is actually doing the image pre-processing thing, the extraction, the feature. So what it actually does, it fine-tunes it for you and transfer learns. So while training the DCNN, as I showed in diabetic retinopathic prediction, here also I'm taking the ACS fashion image. I'm trying to do transfer learning and fine-tuning, so maybe I'm training just the last 2-3 layers, and it reduces that step a lot. That's all.
My question was the RNN. Like, why did you choose to use an RNN? Because it looks like many layers sharing the same weights. Right? Is that basically?
No, it learns in stages, so it's not the same weights. Every time you predict something out in one layer, you actually are. So the convolutional network is one thing. You do it first, and then the final whole feature space you transfer to the LSTM. And the LSTM, what it does, it actually tries to do it in stacks, right? So it first learns and predicts something. Then the next time it goes, it actually takes the predicted tag along with it, and then learns on new features. Just one second. Yeah, it learns on new features and predicts new tag and combines it with the predicted earlier version predicted tag and predicts a new tag, and then again tags it along. So that's how it tries to create. So it knows about the checked blouse that I showed you. It would talk about it's a red checked uniform. So it learns about red. It learns about checks, it learns about uniform, so it can then combine all three and say, I think it's a woman wearing, I did not put any person information in there, but the one which we made available, the cognitive API, if you go and play with it, it will tell you, I think it's a woman wearing a red checks uniform. So, yeah. Yes?
I have a more pragmatic question.
Yeah.
Obviously, the bite of the diabetic example
Yes.
give it to a doctor and say, make this up.
Yes. Yes.
Maybe that would be useful decision like I know operations and other things, but like, is like uncertainty more here? I mean, like if they came to you and said you gave a prediction and the doctor said, well, how sure you are about your prediction? Like, you need something more.
No, so I'll give you an example where this is actually used. It is used, the one which I described for the stroke thing. So it's being used in emergency rooms. So there is, or DHA, DHA is also using it, planning to use it, where there is very less availability of doctors. There is just first aid medical caregiver. So suppose you're on field, you have very restricted medical facility, just you have an MRI machine, and there is maybe one doctor in a remote place handling the whole thing, everybody. So it's very difficult for doctors to come. If you have a stroke, you are brought into the field, you just go through an MRI, and then you are placed in the emergency room for hours before somebody can even start or initiate the treatment. There can be two types of stroke. There can be a clot, there can be a hemorrhage. There are two types of agents you can give. A clot can give a thinning agent, and the hemorrhage will need a clotting agent. If you have a clot, if you give a clotting agent, if you predict wrong and you give a clotting agent, the person dies instantly. So in that case, the doctor's input is very essential. Yes, I'll go, just one second. Yeah, so the doctor's input is very essential, but it actually helps the nurses, to give a smaller doses of TPA, a thinning agent. If the machine says, I think of the software, they feed the raw MRI to the software and says, I think I'm 99% sure it's a clot. Then the nurse can actually give a thinning agent just to start the process and stop the person from dying. Yes. Yeah. Okay. So I'll just stop here. Maybe I'll take your questions outside.